So I'm going to start this little, what kind of questions can we see about end behavior with a brief aside about calculus. So the very first section in a calculus class is limits, which our end behavior is a limit, right? It is talking about as our x approaches something, what happens with our y's, what happens with our function. And so when you first do this in a calculus class, you do a lot of this stuff by numerically. You start plugging things into a table. So the first function here, we know the end behavior of a quadratic with a leading term that's positive or a leading coefficient that's positive. But let's pretend we didn't. Let's pretend we didn't have this beautiful graph. What you do is you type in and you plug in numbers and you keep making those numbers bigger because we want to see what happens as we go towards, right, as our x approaches infinity. And so you just keep adding zeros and you go, okay, it's getting bigger and bigger. It's getting like it's infinity. Cool. And then you do the same thing on the other side. You say, well, what if it was negative 10? All right. What if it was negative 100? And you keep getting bigger and bigger numbers that are positive. So we know we're headed towards positive infinity. So this is what we are actually doing in this calculus class is like, okay, let's plug in, right? If we don't know what the graph is, we can plug in values. And what's happening here is it doesn't matter if I change this middle term to minus 100x. At some point, the squared thing is going to be bigger, right? Sure, the second term, the minus 100x, is larger in our first values, right? Until I get to about x is 100. Because here I'm going to get 100 times 3, and that's my positive bit, minus 1,000. Yeah, of course, this is going to still be negative. But as soon as I get to 100, this first term is going to overpower the second. As soon as I get to a number bigger than that coefficient on the next term, I'm going to beat out what's happening in that linear piece. So this is why that descending order is so important and why our leading term controls everything. Because whatever number you write here, as long as I plug in a number larger than that and square it, I'm going to beat it out. And that is true for any term that the degree higher, that's all we need. So anyways, 22 should be straightforward. We just saw that. If we really wanted to write that in behavior, we can write it either of our two ways. I'll stick with the pre-calculus way for now. As we went towards positive infinity, as our x's got really large, our y's also got really large, right? We could even sketch this. We could see, we know this is a parabola. I'm not even going to figure out what it's a parabola opens up. It's fairly narrow. I don't care. They didn't ask me for that. So in fact, let me go ahead and move this over to the side that it matches. On this side, we have x goes to infinity, y goes to infinity. And on this side, our x is approaching negative infinity, but y is also getting really, really large and positive, just like it was on the other side, because we have an even power, which means our function is going to have end behavior that's the same on both sides. And then we have a positive coefficient, meaning that we're going to go to positive infinity. Cool. Now, I actually really like 23 and 24 because sometimes we get factored versions of polynomials and students struggle with thinking about the end behavior or they want to like expand the entire expression. And expanding an expression is pretty dang straightforward now that we have all these cool solvers that will do that for us. But we don't need to expand an entire expression to figure out what the leading term is going to be. So 23, not so hard. All we'd have to do is distribute that x squared to everything. So hopefully we recognize that our leading term when we do that is going to end up with 2x to the fifth. So if we think about what that graph is going to look like, it's got an odd degree and it's a nice pretty positive. So we're going to have something that looks like this. There could be a bunch of stuff happening as long as it's smooth and actually a function. I kind of like went over myself. As long as it's smooth and continuous, something's going on there. But all we care about for this is the end behavior. And this one says as our x goes to positive infinity, our y also goes to positive infinity. And as x approaches negative infinity, y approaches negative infinity. All right, so 24. This is why I chose these questions out of the OpenStax book. 24. We could use binomial expansion to figure out what this entire thing looks like, but that's tired and annoying. What we should recognize is that if we were to I don't know, evaluate, I don't even say evaluate, just but to expand this, to distribute this, we'd end up with this 7 times dot, dot, dot. I'm not even going to do it. I can't. It hurts my heart. Dot, dot, dot. And yes, 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 there'd be a lot of stuff going on. But the only piece that matters, the piece that's going to give me my leading term, the only part of this binomial I care about for my leading term is the negative x, right? If I multiply that negative x by a 2 in any of the like other binomials when I expand this, well, it's not going to have the largest power. The largest power might, right, if I'm writing this in descending order, is when every negative x is multiplied by itself. And that only happens one time in the binomial expansion. So we end up with negative x times itself 7 times for our leading term. And a negative raised to an odd power stays negative. So we should recognize, hopefully, maybe, that in this one, we end up with a negative x to the 7th power. So again, we could sketch this out if we want to visualize what's happening here, but we're going to have that exact opposite thing happening as what we had on the previous one. Now, as x goes to negative infinity, y goes to infinity. And as x goes to infinity, y goes to negative infinity. And of course, I mean, this is silly in a day and age. You can type this into Desmos and just look at the graph, but can be helpful, especially in a 150. A lot of times you're not going to have access to this. I will talk about this too. The other piece that you can easily find without doing the entire expansion here is our constant term, because that's only going to happen when all the 2's are times each other. So we may not know what all this inside pieces are. We should, because we should know dynamic, but that expansion, but we will know that we're going to get 2 to the 7th power as our final, our constant term, right? That last term. So there'll be a 128. And if I really wanted to chat some more about that, the 128 by itself, if I plugged in zeros for all the x's, that's where I would end up. So that constant term is always going to be your intercept. So there's a lot of stuff that we can see by just looking at that first and last term. And or even if this was an expanded version, right? If we had something like x plus 3, 2x minus 5, I don't know, 7 minus x, something like this, I can go ahead and just quickly look, find my leading term by taking all of the variable terms, multiplying them together. So my leading term is going to be negative 2x cubed. And I can find my constant, that y-intercept, by multiplying all of the constant terms together. I like how I chose this thinking I could multiply 3 times 5 times 7 in my head. It was cute. I'm filibustering now, so I can go look it up. Okay, I was right, but I wasn't confident. So if I were to sketch this graph, I actually, and we can talk more about it because we actually know more, but we could write this and be like, okay, for this graph, whoop, whoop, we know it's negative leading coefficient, odd degree, so we know the overall end behavior doing this. We know the intercept is some gigantic negative number for the y-intercept, right? I guess I'll write these in the colors they were. So we found our end behavior here based on that. And we're going to get there in a second. I'm going to have to split this video because I've gotten so excited. I love graphing polynomials. But we actually know the zeros as well. There's a whole section that's coming up, 2.6, which is about finding zeros. But in the 3.3, we talk about intercepts. If this is our function, f of x is equal to this, I can see when this is equal to 0. It's equal to 0 when any one of these factors is equal to 0. That is that zero factor property we used back in solving quadratics, right? So when this happens whenever x is equal to negative 3, x is equal to 5 over 2, or x is equal to 7. So we know our x-intercepts as well. There's one here, there's one here, and there's one here. And then we learned about multiplicity, right? When we did our activity, and I'm not going to get into that now, but since all of these are just multiplicity 1, we're going to pass through. So we could go ahead and sketch this entire graph now. It's doing this, passing through there, going here, ending up there. We've got our entire function sketched just based on looking at a little bit of information. This gives us even more information, right? We don't know that this is the lowest point. It might get lower somewhere else, but we could talk about, intervals. We can't say where the intervals of decreasing and increasing are, but we can talk about how many turning points this thing has to have. We know it has to have 2 turning points because of what's happening here in our graph. That's the only way to get down, to cross that axis 3 times and have that in behavior. So yeah, we have lots of cool stuff that we can start sketching and knowing must be true about our function.